Hello everyone, welcome back to the channel. In the previous video, we have seen the concept of wavelets and how we can use this wavelet concept for flood risk forecasting. In this video, we will be developing a data set of precipitation which represents a whole basin. So we'll be using a Thiessen Polygon method to calculate this precipitation so that we can use this precipitation for prediction of discharge. So firstly, in this video, we will see the basin details and the rain gauge details in ArcGIS and use the concept of Thiessen Polygon there and get the results from the ArcGIS and use them in Matlab so that we can develop this data set of Thiessen Polygon precipitation. This obtained precipitation we'll use in our next video for developing a wavelet neural network model for prediction of flood in that basin. So our first step is to input our shapefile of the basin into ArcGIS. As you can see here, I already have the shapefile of the basin which I'm going to use. I've just dragged it into ArcGIS. And if you notice here, the units are already in meters. Generally, you need to georeference the shapefile or the raster file or whatever the dataset which you are using. So I have already georeferenced the shapefile, so we are having it in meters. The steps which you can follow to do this is go to geoprocessing, Arc toolbox. Then once the toolbox opens, you can go to data management tools, projection and transformation. If it is a raster file, you can directly do it from project raster. Next, then you can go to define projections, where you will be defining, you'll be giving the data set. Let's say here it is Vamsadara final. So you'll be choosing that, and then when you get the selection done, you can choose the coordinate system. Generally, because I have already done it into projected coordinate system, it is showing a UTM zone, whereas generally it will be in a geographical coordinate system. And then once you define the projection, you need to go to project and then project the data set so that it is saved into a UTM zone, which is a projected coordinate system. So I have already done this procedure. So that is the reason why we are having meters here instead of decimal degrees. So the next step after having the shapefile is to know where our precipitation gauges are. I'm doing this case for India. For India, there is a website with name Indian Meteorological Department, where all the data sets are present from 1901 to 2020 or 21, probably maybe now. So I've already downloaded the data set and I have created the shapefile of the grids. So if I input the grids here, you can see that. Let me zoom to layer. If you see here, these are all the data sets of precipitation gauges in India, and what we need now is only the gauges which are in our basin. So one thing we can do here now is we can clip the files of precipitation gauges with the base as our Vamsadara Basin, so that we get all the points inside that of the basin. So to do this, we can search the tools called clip, where once we click it, we can go to clip analysis tools, and the input features which we want to clip are the gridded precipitation data, and the clip features which we want to do are up to the scale of this basin. So we can choose this, and then you can choose the output data extent, which is the place where you want to save it. So for now, I'll just save it in the documents folder, but generally when you are working with a project, it's preferable to put it in your project file so that it does not get replaced or misplaced. So once I click OK, the projection starts working. It just generally takes about a few seconds to a minute a maximum, and then you'll get the result of the projected data here. So if you see here, if we remove the overall grids, we can see that around 1, 2, 3, 4, 5, 6, 9, 12, 15 points are inside our basin of our interest. So these are the points. If you see the attribute table here, these are the 15 points which are in our basin, and these are the lat longs of our data set. So the next thing which I'll be doing before getting this Thiessen polygon is I'll be extracting the data set of these lat longs from the data set which I have obtained from the Indian Meteorological Department. So using these lat longs, I'll be getting the precipitation values of all the points which are inside this basin. So once we got these points, the next step is to develop a Thiessen polygon. So if we go to our search tools and press Thiessen, by searching it, we can get create Thiessen polygons. So the thing we need to do now here is we already have the points called IMD clip 2 which are inside the basin. We will use those points and create the Thiessen polygon. One thing you can do here is, in order to prevent, generally whenever you are doing a Thiessen polygon, most of the time it goes beyond the extent of our basin. You can either clip it to have it calculate only the area in the basin, or you can try to create the extent here in the environmental settings, putting the extent to the Vamsadara Basin. So the reason why we are putting the extent here is so that if you see in the background, if we don't put the extent up to the basin, the area is calculated with respect to these points which are far interior in the basin. So most of the area will be omitted. Let me show you what happens if we don't put the extent here. So if I just put the clip points here and press enter, you can see that the area of the basin here is not considered into the calculation of the Thiessen polygons. So in order to prevent this, we will use the environments here. As you can see here, we will go to the processing extent and say please do it until the extent of the basin. So even if we put this, it goes beyond the basin. If you see the result here, one thing which we can do here is to prevent any error from our part in calculation, we can clip the extent so that we don't get any extra area. So what I'll do here is I will take this created Thiessen polygon 3, which is our last thing, and clip it to our Vamsadara Basin so that we get all the area which is interior to the basin. So if we see here, this is our final result, and these are the areas which are being covered by this one gauging station. So if we know the area of this station and multiply it with the precipitation data, which is precipitation times area, and do it for all the areas here, we will get Thiessen polygon. As you might know, the formula is P1A1 plus P2A2 plus P3A3 and so on till n by the overall precipitation, which is P1 plus P2 plus P3 so on till n. So this is the formula of Thiessen polygon. So in order to multiply it to the precipitation now, we need to get the areas of the each precipitation gauge which is covering. So if we now go into our attribute table, we can already see that some shape area is being calculated, but we do not know exactly what are the units of this area, and we don't know the accuracy of this area. So the one thing we can do is we can add field and write area calculated, and we can use the format of double so that we can get more extent of decimal accuracy, and press OK. So as you can see here, an area calculated is created without any area data set. So the thing we can do here is we can right click on that and calculate geometry, where it will ask us to say if it is okay for us to edit this session. We can say okay here, and then if you see here the area property, we have different properties like perimeter and area. We can calculate the area. Our projection coordinate system is showing correctly, and instead of square meters, because these basins are quite big, several kilometer squares of area, so instead of having a unit of square meters, we can put a unit of square kilometers, and then when we press OK, it says yes. If we see here, the area is calculated, which is in square kilometers. Let's say click it here. So if you see here, this is the area of this square, which is around 729.65 kilometers square, and so on. We have areas of different different parts which are being governed by different rain gauges. So in this way, you can calculate the areas of each precipitation gauge influence zones. So now we got the areas of all the zones for each precipitation gauge. The next thing we need to do is we need to see which rain gauge is having which area. So this is our first point of 18.5 and 84. So let's find out what is the area of this point. So again, go back to the attribute table, and if we see here, we'll just try to find the one. Yes. So if you see here, this location has an area of 569.32 square kilometers. And next, this is our second point, the second gauge, third gauge, and so on. We can follow the input FID here, as input FID represents the point of each precipitation gauge in order. So we use these points and note down these areas in a correct order so that we can use these areas in Matlab. Once we got the areas, the next thing we need to do is put our precipitation dataset into Matlab. So as I've mentioned earlier, I have already got the dataset from IMD, and you can see here I have got the daily rainfall datasets from 1901 to 2019 for all the points of India. So if I just input it here, this is the dataset of precipitation from 1901 to 2019 for the whole India. As you can see, there are around 4,626 gauging stations in India. So our work now is, after knowing the lat long of the dataset, one thing we can do here is use the lat long files so that we can get the exact dataset. So one thing we can do here is, if you see the Excel sheet here, we have all the lat longs here, and the number of row here represents the number of column in our Matlab dataset which we need to extract. So I will manually note down the rows of the data which we need to extract. So if you see here, these are the columns of the dataset for each lat long of our 15 rain gauges, which I have noted down manually. So we will use these columns to extract the dataset from these 4,626 columns. So to do this, we can simply write a few lines of code which we can use for extracting this dataset. So I've already written a 3-line code which we can use for extracting this dataset. So let's see what this code is and how it is extracting the data we need. So put it simply, I'm just running a for loop so that I can save 15 columns of data, which is our 15 data sets which we want to extract. So to do this, what I'm doing is I'm just writing a name called data. This is the file name which our result will be saved, and I'm asking it to be saved in each column. So let's say when I is equal to 1, the data which we are extracting will be saved in the first column. When I is equal to 2, the data will be saved in the second column, and so on till the 15th column. So this is how the data is saved. So let's see how the data is getting extracted from there. So this is the name of the file where all the data sets are, which is 4,626 data sets are. So I'm going into that data and I'm saying I need all the rows. Here semicolon represents all the rows, comma. Now I'm specifying what columns do I need. So in order to tell that to the code, I'm saying to know the columns, first go to the data set called need, because that is where I have saved the needed locations of the data which we will be extracting. So what does the code do? The code goes into need and it goes to the number of rows, because here the data set are in row matrices, 15 rows and one column. So I am saying it to go to the first row. So what happens here is it goes to the first row of first column, which is 951 value. So in this data, it will go to 951st column, and that data will be saved here in our first column. So in this way, for each run where I is equal to 2, 3, 4, so on, it goes to different matrix, which is, if you see here again, it will go to 996, 997, so on till 1190. So it will go there and save the data as data. So first we'll try to evaluate this. So if we see here, the data is saved in the name data, and you can see that there are 15 columns of data which are extracted, which are from the rows which we have mentioned here in the need file. Now we have our 15 data sets of precipitation which represent the points in Vamsadara Basin. Once we got all the precipitation data set, the next step is to multiply it with area so that we can get our Thiessen Polygon precipitation. So let's first create a file called area here so that we can create and copy paste our areas. So if we see here, these are the areas which we have obtained in ArcGIS. So I will just copy these areas. As you can see here, they are according to the FID. So they correspond to 1, 2, 3 up to 15 points accordingly. So let's directly paste our data set here. So these are the areas which we will be multiplying with precipitation. So the next thing we need to do here is we can multiply our data using a code. For that, we will use again a for loop so that we don't have any issues multiplying and it makes our work easier. So again, we will use a for loop and write I is equal to 1:15 because I'll be multiplying 15 data sets here again. And now I'll save it as Thiessen so that we can save it as Thiessen precipitation, and again we will save it into different columns because after multiplying it we have P1A1, P2A2, P3A3 and so on till P15A15. So what we'll do here is now we have the data sets and our data are called data, and I'll ask it to go to all rows comma ith column. So now it will go to our first column in our data and then multiply it with area of which row again we need to get our first row. So because here again we have a row matrix, so we'll multiply this part with first column, this part with second column and so on. So this is how P1A1, P2A2, P3A3 and so on will be obtained. So using this command we can get the Thiessen Polygon precipitation, which is P1A1, P2A2, P3A3 so on till P15A15. So when we run these lines, we can see here that we got the precipitation data sets which are multiplied here. You see the value is so high because it is multiplied with area. So once the Thiessen precipitation is calculated, we need to get the total sum of precipitation, which is P1A1 plus P2A2 so on till P15. So to do that, we will have a row matrix calculation instead of column because we need to add up all the rows in the first row and get one value of precipitation. For the second row, another value, so on till all the rows. To do that, we will write a for loop again, but here instead of using a column matrix, which are 15 columns, we will use the number of rows. The number of rows here 4, 3, 4, 6, 4. So these are the number of rows which we want to add all the data of the 15 columns. So what I'll do here is I'll write as sum of P, and I want a row matrix of one column and the so many rows which we mentioned above. So I will say is sum, add all the Thiessen precipitation rows, which is the first row of all the columns. So what does this statement do? It sums all the columns of first row. Again, we see here it adds up all these values which are in the first row for all the 15 columns and give you a result. So if we put this here and write end, and once we run this here, we can see here that sum of P, we got only one row with these many values. So if you see here, it is 5,000 and 50416. So if we go to Thiessen precipitation, you can see 1000. For the third row, 600, 400, 600, 1000, 1000. So we add up all these row and we got the 5000 value. So this is our upper part of the formula. So again, if we see the formula here, P1 A1 plus P2 A2, so on till P15 A15 by A1 plus A2, so on till A15. So now the next step is to calculate areas. To get the area, we can directly go into Excel, and if we see here, we can directly write sum of all the rows here, and if you press enter, if you see here, this is the total area of our basin in square kilometers, which is 10,442. So what we can do here now is we can directly divide this thing per each row again. So instead of writing a new line again here, we can use the same principle which we used here. Instead of having a precipitation, we will say OP, which is overall precipitation, and we will go to each row, but we will not do sum here. So let's replace this statement with sum of P, because that is our precipitation value, and we'll ask it to go to the first row, which is the ith row here of first column, because we only have one column, and then divide it with 10442, which is the total area which we have calculated. And so this is our overall precipitation of each row. Once we do our evaluation here, and you can see the OP here, this is the precipitation which represents the overall precipitation of the basin, which is the Thiessen Polygon average. So we can use this precipitation as an indicator of overall precipitation in the basin for which we calculated the Thiessen Polygon. So this is the data we'll be using for developing our model of Wavelet Neural Network. So in this way, we can use our GIS and a few lines of code in Matlab to easily get our Thiessen Polygon dataset. You can do all these steps in a single code itself, like combining these steps into one command, so that you don't need to write these many lines. But for the sake of explanation, I've created each step separately, but generally it is preferred to combine these two because we use the same number of rows here. So this way you get a Thiessen Polygon dataset. In the next video, we will do our forecasting of our discharge with Wavelet Neural Network using this Thiessen Polygon dataset.